So now we're going to discuss leaching and the things that concerns leaching. This is still under separation processes, part of the separation process. So let's go first to the basics, and that's the definition of the process itself. So when we speak of bleaching, it is the extraction of a soluble constituent from a solid by means of a solvent. So this is one very different kind of separation because this time we're not dealing with fluids, but rather one is a solid and another one is a liquid. So the soluble material in this case is dissolved from its mixture with an inert solid by means of a liquid solvent. So your mixture here is your solute, which is in solid form, together with the inert solid that it is mixed with in the solid matrix. Now your solvent, which is liquid, is going to dissolve this particular solute and separate it from the inert solid mixture. Now there is this particular type of leaching process wherein the solvent is just pure water. So in this case, the leaching process is also referred to as washing. So when we're using water as the solvent, it's referred to as washing. Now, what are the principles of operation of the leaching process? So number one, there has to be contact. So the solid matrix consisting of the solute and the inert solid it is mixed with has to be contacted with the liquid solvent. Next is we need to separate. So after your solvent separates already or dissolves already rather the solute in your solid matrix, it is to be separated from that matrix. So leaving the inert solid behind. Now what happens next? So this is a three-part operation. We need to extract or separate the mixture of the solute with the solvent, which is another process in the separation process. So normally, our solvent needs to be separated from the solute again after leaching because they need to be separated. You need to separate the solvent that you use from the solute that it dissolved from the solid matrix. What about the solid, the inert solid? The inert solid that was separated from the dissolved solute will be washed further. So the term used is wash further so as to increase recovery. And that is to recover as much amount of solute that it has so that when it is already spent solid, then there isn't much of a solute remaining on it. So to increase recovery, we need to wash. Your inert solid needs to undergo further washing. That way, recovery is increased in terms of the solute. So you have the solvent interaction with the solid matrix is in terms of contact. Then we separate desired substances from solid matrix using solvent. This is the part wherein after dissolution of your solute from the solid matrix happens. And then in extraction, the extracted desired substance for collection undergoes, as I said, extraction. So the solid needs to be separated from the solvent that take it out from the solid matrix. So that is in the case of this three-step operation, principle of operation for leaching. Now, the process can either be carried batch, semi-batch, or continuous and may be operated at an elevated temperature. Now, it may be operated at an elevated temperature to enhance the separation or to enhance the dissolution of your solute from the insoluble solid matrix. Now, flow, most of the time, especially in multi-stage leaching processes, is either counter-current or cross-current. Now, the amount of soluble material removed is often greater than in ordinary filtration washing, and the properties of the solids in this case may change considerably during the leaching operation. Actually, in some processes, a simple filtration washing will already dissolve the solute from the matrix of the insoluble solid it is mixed with. However, in terms of recovery, there is much greater recovery if we're going to use the process of leaching. Now, there are four very important factors to be considered in the process of leaching, and that these factors are the particle size, how big the sizes of the particles are, the characteristics itself of the solvent, the temperature, because it was mentioned in the previous slide that at some point some leaching operations have to be carried out at elevated temperature, and there are also some leaching operations wherein there is some form of agitation, all with the purpose of enhancing recovery. So these are the very important factors to consider in leaching. Now, in terms of temperature, they are adjusted to optimize solubility and mass transfer. So it's a given already and mentioned on the other side, all for the greater objective of enhancing recovery. Now, the contact time and area, this is referring to the solid matrix itself. The solid matrix itself consisting of the solute and the inert solid B. To refer to that inert solid as B. So liquid to solid contact is essential for the extraction to take place, and we need to maximize contact area per unit volume so as to reduce the requirement for sizing of the equipment. So we need to maximize contact area and even time of contact. That way, we need not design a very large leaching chamber or vessel. This is the primary reason for that. Now, in terms of the characteristic of the solvent, so it's very important that your solvent will selectively dissolve the solute only, meaning your B, your inert solid B in the matrix of the solid should not be soluble in your solvent. So solvent selection plays an important role in solubilities as well as the separation steps that follow leaching. So mentioned already that there's an extraction step that follows after leaching. Nearly all leaching equipment employ some type of agitation to aid in mass transfer and to ensure proper mixing. Now, as to the process overview, although we already are guided by the three steps mentioned a while ago in the second slide, in a typical leaching operation, the solid mixture to be separated consists of the particles of the solute we represent as A and the inert insoluble solid carrier B. So our matrix, solid matrix, is only consisting and assumed to be only consisting of these two, solute A and the inert insoluble solid B, the one that carries your solute. And then we represent our solvent as C. So the solvent C is added to the mixture to again selectively dissolve A. So it's only going to dissolve A, and your inert insoluble carrier solid B should be unreactive towards C. Now, the overflow from stage to stage is free of solids and consists only of the solvent C and the dissolved solute A. Now, in leaching class, comparable to extraction, in extraction, we have the term extract and raffinate. The extract is removed on top, the raffinate is be removed at the bottom of your extraction equipment. Now, comparable to the extract in the process of leaching is what we call as the overflow. Okay, the overflow consists of the solute A, which was dissolved by your solvent C in your leaching process. Now, the raffinate in extraction is comparable to the underflow in leaching. So, raffinate in extraction is underflow in leaching. It is the byproduct because the main product actually is the overflow, because this is where you have your solute A. In the same way with liquid-liquid extraction, that your main product is the extract and your byproduct is the raffinate. So going back to this, the underflow consists of a slurry of liquid of similar composition in the liquid overflow and inert insoluble solid carrier B. So your slurry or your underflow consists of a slurry of the inert insoluble solid B that was not dissolved by C and a solution having the same concentration as the overflow. So whatever is the solution of concentration of the overflow, that is the same concentration of the solution that remains with your solid in your slurry. Now, in an ideal leaching equilibrium stage, because in leaching we are also using the concept of equilibrium, it is assumed and it is always assumed that all the solute A is dissolved by solvent C, and none of A will be carried by your insoluble solid carrier B in your underflow. So all the A should be in the overflow, and what remains in the underflow is just the inert insoluble solid B. Now, the only presence of A in the slurry is the A that is present in the solution in your slurry. So remember that your underflow is in the form of a slurry. So your solid together with the liquid, that's your slurry. So the liquid has A on that because the composition of the liquid in the slurry is the same, or the concentration rather of the liquid in the slurry is the same as that of the overflow liquid. These are the things that you need to know regarding the leaching process. Now, the mass ratio of the solid to liquid in the underflow, so the amount of solid that is present in the underflow divided by the liquid that is retained by the solid in the slurry in the underflow, is dependent on the type of equipment used and the properties of the two phases. The two phases that is being referred to in here is your feed, your solid feed, and your solvent. Now, leaching is essentially counter-current mentioned as well. It could also be, however, cross-current. Now, in industrial leaching, solvent and solid are mixed, allowed to approach equilibrium. That is why there is also this concept of equilibrium applied in leaching, and the two phases are separated. Now, in extraction, we call the dispersed phase as the solvent phase, and we call the continuous phase as the water phase or the raffinate phase. So in here, we have also what we call as the solvent phase. So our solvent phase is, of course, where the solvent is. So referring to the overflow and the underflow, our solvent phase is the overflow. This particular phase becomes more concentrated as it contacts in stage-wise fashion the increasingly solvent-rich solid. Now, the underflow, on the other hand, becomes less concentrated in the soluble material because the solute is already carried by the solvent in the overflow, and as it moves towards the fresh solid phase. So this is in the case of the scenario here, which was referred in the second uh, bullet, that it's countercurrent in flow. And most of the time, it's really countercurrent. Now, there are two categories of leaching equipment. So we have the percolation, wherein the liquid is added to the solid. In this case, the solvent is contacted with the solid in a continuous or batch method. This is popular for extreme amounts of solids to be processed. So if a very large amount of solid is to be processed, then we percolate the solvent to the solid that contains our solute. So that is why it's referred to as percolation. The other one is dispersion. So this time, it is the solid that is being dispersed to the liquid. So your liquid is in this case, is the receiving phase. Solids is being added here to the liquid. The solids are usually crushed into smaller pieces before being contacted with the solvent in this case. Crushing of the solid enables us to increase the mass transfer area, and if it is increased, of course, recovery will also be increased. Now, this particular method is popular when an especially high recovery rate can economically justify the typically higher operating cost. So between the two, dispersed solid type of leaching is costly. However, dispersed solid type of leaching has a higher recovery than percolation type. Now, of the two, what is the advantage of the percolation? Because it seems like all the advantage is here. Now, it has high recovery, although it is costly. The advantage of percolation leaching is it can process a large amount of solid. Since it will process a large amount of solid, it is expected that recovery, of course, will not be as improved compared to the second method, which is dispersed solid bleaching. So we only have these two categories of bleaching equipments. Okay, either the liquid or the solvent is added to the solid, or vice versa, the solid being dispersed on the liquid solvent. Now, as to the equipment, so you could see actually these equipments in our general reference book, specifically in Jan Cooklis. McCabe also has these particular equipments in terms of other simple illustration. So we can have a fixed bed bleaching, we can have a moving bed bleaching, and we can have a dispersed bed bleaching. So as for fixed bed leaching, so it's a very simple equipment wherein you're going to put there the solids, and over time, the solvent present in the equipment is going to extract the solid from the solid. So the example stated here is the solution of the solid content of sugar, specifically sugar, in the plant we call beet. So used in beet sugar industry, and this can also be used for extraction of tannin from tan bark, and even in extraction of pharmaceuticals from barks, tree barks, and seeds. So in this case, we have a fixed bed wherein the solids are introduced into the bed. Okay, the other type is moving bed. So it is the bed that is moving. So in this case, we can either have what we call as the Bullman extractor. So the Bullman extractor, we have two. One of these is taken from John Couples, the other one is from McCabe. So it's an enclosed moving bed bucket elevator device where there are perforations in the bottom of each bucket. So as you could see here, you have the pure solvent being introduced on each of the buckets as the bucket passes this particular portion of the assembly. So as this bucket goes to this particular solvent introduction section, the solid inside the bucket are being washed by the pure solvent. And as the process of washing proceeds, of course, the solute gets dissolved, the solute present in the solid. It could be something like this also. It is the solid here is being fed in this particular bucket, and it's moving, in this case, co-current. So this one goes down. The solvent, on the other hand, is in this section. You can see this rod here. This is where the solvent is being introduced to the bucket that has been filled already by the solid. Being filled here, then you have the bucket being filled straight with the solvent. So the process continues. So all of the buckets go downward, and then the solids release, and then when they reach this part, you could see this one. This is the part wherein the buckets is releasing the solids. So it's, shall I say, going upside down. That way the solid content will be dispensed in the container here below. And you have some elevator here, screw elevator, that will take out the spent solid. The solid wherein we have already taken out the solute. So since this will be now emptied, then it will be again filled by this, shall I say, entrance of the solid part of your equipment. So this is where your solid is being fed. Now, another moving bed example is the Hildebrand extractor here on the right side, wherein instead of buckets, which can either be closed or open, you have here screws. So consists of three screws arranged in a U shape. So a screw conveyors arranged in U shape, and the solvent flows, in this case, counter current to the solid. So in here, you could see that the solvent is introduced in this portion. So then the flow would be downwards, whereas the dry feed is introduced here. So the screw carries the dry feed up here, and the solvent keeps flowing down countercurrent to the moving bed of solid. In the process, your solvent gets to dissolve the solute present in your dry feed. Now, it could be as enclosed as this one, but this is also still Hildebrand extractor taken from a cave. So solids are introduced here, solid feed, and you have the solvent introduced at the bottom. So still, the flow in this equipment and in this equipment, in this one is co-current flow, while this one is counter-current flow. The mycela class is a mixture. The mycela that you see here, the term mycela, is a mixture of your solvent with your solute already present on it. Now, these are the two types of equipments under the moving bed category. Then we can also have what we call as dispersed bed leaching, oftentimes used in what we call as thickeners. So dispense solid, so that you have already in these thickeners your solvent. What happens are your solid is being dispensed continuously. This is the part where we introduce the solids to the thickener here, and then your, shall we say, the solid is being raked off from this particular thickener here, okay, at the bottom part of your thickener. Now this is where your fresh solvent is introduced continuously. So the extracted solid, so the solid coming from here is again introduced on the second thickener and again onto the third thickener with the purpose of extracting as much as possible the greatest amount of solute that could be extracted or leached from the solid. The spent solids are of course withdrawn here, so you can see the arrow here. As for the concentrated solution, it's being withdrawn in this side. So your fresh solvent is in here, then you have your concentrated solution withdrawn on the last part of, or in the first part here of your thickener series or system. Now this one is dispersed bed leaching because your solid is being dispersed through your solvent liquid in the equipment already. So it is your solid that is being fed to the equipment. Now, as to the industrial applications of bleaching, so you can see here the extraction of sugar. This is example of a beet, a plant beet, where sugar could be leached out or extracted using a simple case of warm water bleaching. In here, we have a picture of vegetables and oils. So the extraction of oils from seeds and from plants is also a process of bleaching. And in here, in the most, shall I say, highly economical industry, shall I say, in terms of economics, this is the one that has the big money. So the metal processing industry, however, is really environmentally non-friendly because we take out soil and we mine the soil, we mine whatever is present in the soil and take out the precious metals or minerals present on it. So in the case of metal processing industry, we also use leaching. So you can have here as an example the beet plant wherein we form sugar by a simple case of washing with warm water. Then we can have also the extraction of vegetable oil from nuts, beans, and seeds using organic solvents such as hexane. So your solid matrix are these nuts, these beans, and these seeds. And we also have in the last part the extraction of gold from ore or the extraction of some precious metals from mined ore. In the case of one of our benefactors, the Coral Bay Nickel Corporation, they are using high pressure acid leaching, the HVAC process, to take out nickel from a mined ore. It's very expensive. The process is very expensive because it's using a lot of energy. So it's catalysis, using catalysis, high pressure acid leaching. You break down the ore, that way you can take or leach out nickel from it. Okay, so that's it. Now, let's go now to the principle of equilibrium applied to leaching before we go to real problems solved using the principle of material balance. So we only use material balance in leaching. Now, solvent forms a liquid solution. The carrier may be totally immiscible. So in the case of equilibrium applied to leaching, our solvent is liquid, so it forms a liquid solution that remains immiscible with your inert solid B. Now, some solution is normally retained by the solid, and that's the reason why we have what we call as the slurry. And that solution has the same composition as the liquid solution that was mentioned here in the first bullet. When the amount of retained solution is constant throughout the process, we have what we call as a constant solution underflow. Take note, when the amount of the retained solution retained by your solid, that is in your slurry, is a constant throughout the process, the same process is referred to as a constant solution underflow. When, of course, it varies, so variable underflow exists when the amount of retained solution is a function of concentration. Now, in the third bullet here, we expect that even though the concentration of the solution changes, we expect that the same amount of solution is being retained by your solid in your slurry, even though it is a given that concentration changes over time. But in the case of variable underflow, this particular amount of solution retained by your solid in the slurry is affected by the change in the concentration. So as such is referred to as variable underflow. This time, the amount of solution retained is a function of the concentration of that same solution. Now, the stages here in multi-stage leaching processes are numbered by the flow direction of the solid. So wherever is the solid being introduced, that is stage 1. So we number it as stage 1, the part of the process wherein your feed solid is introduced. As to the assumptions, I have already enumerated the assumptions here, and some I have mentioned in the other slide as well. Solute-free solid is insoluble in the solvent. Flow rate of the solid is constant through the cascade. Take note of this because this is one of the key principles you're using when you do material balance later on. The amount of inert solid present in your feed is the same amount of inert solid that will be later on present in your slurry. We refer to as the underflow. It will not change. Now, your solid is assumed to be all porous and inert so that your solvent is able to come into the matrix of your solid. Your solvent is able to, let's say, penetrate the matrix of your solid and dissolve solid A present on it. Now, the amount of solution retained by the solid in the slurry is dependent on, so we say it's dependent on the concentration. So it's dependent on density and viscosity because the concentration of the solution is also dependent on density and viscosity. So the reason why the amount of solution in variable underflow changes is because our solution as the process proceeds becomes very unique, as such its density and viscosity changes. Given these two changing, the concentration of the solution also changes. In constant underflow, even though this changes, because this cannot be constant all throughout the process, the amount of solution retained by the solid is assumed to be constant. Now, solvent amount is sufficient to dissolve all. So mentioned, I think, in the first slide, all the solute should be dissolved by the amount of solvent used. Now, this one is very important also. There should be no adsorption of the solute on the solid. So meaning your solute initially present inside your solid intermixed in the form of a matrix with your inert solid B or inert insoluble solid B will never adsorb or remain on the surface of your solid. Solution in the liquid phase is the same solution that remains in the solid matrix. We know already how they are made. Okay? And this is how we represent leaching for a single stage process. Okay? We label our solvent still as V, and we label our feed and our slurry as L. So this is our feed solid and this is our slurry. This is our solvent. Now, what do you think is ironic in the illustration? I think you could spot out what is ironic in the illustration. What do you think is very ironic or contrary to, in comparison, if you're going to compare leaching to the other separation processes discussed already? So far, we have discussed gas absorption and extraction and desorption and stripping. What's so different about leaching in this case? If you're going to look at the representation of a simple single stage leaching process,
Ang ano, miss, ang mole fraction, miss.
mole fraction. What about mole fraction? Did
Kaya usual
sige,
ah,
go.
kaya
Go.
usually miss sa L, miss X ang ginagamit tapos other miss B, sa B, miss X na miss hindi Y.
Okay, so that's very correct. So you have a keen eye in there. The B usually from the other processes, and in the other processes, all processes that we will be discussing is always paired with a concentration representation in terms of Y. And our feed or our phase to be processed with that particular solvent has a concentration in X. In the case of leaching, it's the other way around. The solvent will have its concentration represented as X, and the feed and the slurry will have its concentration represented as Y. Now, I just mentioned this now. Kat said the mole fraction. So just like extraction class, just like extraction, we're using mass concentrations in leaching. So since otherwise, if the feed, if the slurry, if the solvent are in terms of moles, then of course the concentrations have to be, of course, in moles. But most of the time, they are in mass. So X and Y are concentrations, which we do not most of the time use moles here in leaching, but rather we use mass. What else have you noticed? What's added here in leaching? What do you see that is not present in the other separation processes? You have the presence of the N. So the N is the concentration of the inert insoluble solid B. Later on, you will know how we write the concentration of the inert insoluble solid B. And of course, you see the B. The B is the inert insoluble solid. So now they are written, if possible, and if given in the schematic diagram. That way, when you do material balance, it's so easy to see the specific information that you can use in determining whatever the problem requires. So this is how we represent our leaching equipment. Now, this is how you represent the concentration of the solid, the insoluble solid B, in the slurry and in the feed. So N is equal to kilogram B over kilogram A as kilogram C. This is how we represent it. A is your solute and C is your solvent. As to compositions of A in the liquid, whether it's the overflow liquid or the underflow liquid, we have kilogram A in the numerator, X for the overflow, Y for the slurry. And the denominator is kilogram A plus kilogram C, just like in here. And we also have kilogram A plus kilogram C in the denominator. Now, what have you noticed about the manner in which we express the concentrations? Aside from, of course, we've seen this already, that we use X for the solvent and the overflow liquid, and we use Y for the slurry, and that's your underflow liquid. What else have you noticed regarding the way we express concentration in this case? Okay, it's notable, as I mentioned a while ago, you use mass. We don't use moles. Another thing, if this is only happening in leaching, we don't use fractions. We don't use percentages, but rather we only have a denominator in the way we express the concentration in terms of A and C only. The denominator does not contain the inert insoluble solid B, whether it's N, whether it's